the 12, and the seismic. What I did, and I sent this morning, basically I collected all the problems that related to the seismic design, or the special design, the seismic design for the special exam, the 2.5-hour exam. And I put them in the form of exam, as you can see here. So these questions are collected from my books. And as I mentioned last time, in order to get the maximum benefit for everybody, let me make sure that the system is working and all of you are here, especially the seismic group. I assume that all of you are here. And also I made it for free for those who are interested to attend for free. I have no problem with that. So and I send the exam, and I will come up with one every week. Even these problems, maybe some of you already saw it before, but we need to make sure that we really understand. But for those who are taking the course, they have the textbook and they have the 6-6, and plus the additional materials. I send it to them about the codes, about the ATC and so on, ATC 20. So the textbook, as you know, this is the one I'm using this semester, which is based on the current code or codes, specifically the ATC 20 and ATC 20-1 and the ASC 7 and so on, ASC 7-16, which already we talked about that. So I taught the course during the first quarter, and the access to the recording, which we call it on demand, is available for those who are who took the class with me and who are taking the class with me this quarter. So the on demand is available for you 24/7. So today is 4/22, 4/12, sorry, 4/12/20, and this is a seismic review. Seismic review, second quarter. So the on demand, which is about 55 hours, by the way, which I taught at the first semester or the first quarter, is available for you 24/7. You can access and you watch it again and again and again. Don't worry, we pay money for every time you watch, but this is part of the course. So if you have any problem viewing the on demand, any technical difficulty, please let me know. Also, at the same time, we send you a USB, green one like this. It has our name on it. It has the 6-6 seismic problems, seismic CBT problems, where you can generate unlimited, in fact, I call it unlimited, which is in fact unlimited. The computer will generate unlimited 55 question exam each, and it is timed for 2.5 hours to simulate the actual exam. This is my 5th edition. I came up with the first edition way back, almost before anybody else in the market, way back when I was teaching seismic for schools here, or the school here, and before I came to Fresno. I was teaching also back in Las Cruces in New Mexico, CSCU Fresno, and New Mexico State University in Las Cruces. So this is my 50th edition. This is the textbook, which is book number 1, and it does consist of 16 chapters. And today I would like to focus from chapter 1 to chapter 5. So today the problems I send, and if I were you, take it seriously, and this is exam number 1. I will solve the 55 questions as if I never saw them before. And I would be glad to go over any problem or any topic. So you're supposed to finish this in 2.5 hours. And you try to challenge yourself, as I always say, because the more we challenge ourselves here, the easy task will be during the actual exam. Okay, so if you look to the first 5 chapters, chapter 1 to chapter 5 of my textbook, you'll find this basically introduction. And if I look to the table of contents, I have a very comprehensive table of contents at the beginning of the book, and also nice index at the end, computer generated index. You will find that chapter 1 is talking about building codes and organizations. I talk about the different codes that they are used or they have information related to seismic. I talked about organizations. And at the end of each chapter, you will find that I'm providing sample questions and supplemental practice problems. And I provide the solution for both the sample problems and the supplemental practice problems. Chapter 2, it's seismic legislation and the Professional Engineers Act. Chapter 3, things start to take a little bit toward the code or the seismic code. So we talked about loads, design philosophies, structure analysis and stresses. Chapter 4, earthquakes, characteristics and basic theory. And the chapter 5 is talking about some terms that we use it a lot in seismic design and analysis. So I talked a little bit about the vibration theory, stiffness and rigidity. So the first 5 chapters, I call them introduction. The heavy stuff start from chapter 6, where we start to use a code, the ASCE 7, for example, specifically, 7-16, chapter 11 and chapter 12, these 2 chapters, talking about seismic building, seismic requirements for building structures. And after that, chapter 7, 8, 9, all the way until we hit chapter 16. Because the code, the current code, as you know, it is the IBC, International Building Code 2018 / CBC 2019. CBC, California Building Code, it depends, or it came from, or based on IBC, the International Building Code. So either one of them. The difference between the CBC and IBC, that CBC, it has A chapters. For example, you'll find chapter 16 and 16A. We don't really discuss or talk about chapters, the chapters of the CBC that it has the A, that it is related to DSA, Division of State Architect, DSA. So we are not really talking, so only the chapters without the A or the straight chapters. You can use it either this or this. This is much cheaper and straightforward and to avoid any confusion. In addition to these two codes, we have the major one, which is the ASCE 7-16. This is the core of the seismic, and you'll find the majority of the equations, the large number of equations coming from this publication. And this publication, we are not, because it's a very thick document. In fact, it has 2 volumes this time. This edition, they came up with 2 volumes. The code itself, and after that, the commentary or the explanation of the code. I'm sorry, probably I did something. I don't know if the camera is no longer, even I did all my best to secure it very well, but it seems to me I hit something, or maybe let me bring the camera back again, because it seems to me the camera is disconnected. Sorry for that. Even I secured it very well to avoid this. Let me try again one more time. Hopefully this time will recognize the software. Yeah, now now it should work this time. I hope so. Forgive me, it's just okay, here we go. Sorry for this technical difficulty. So the ASCE 7 is very important code, and as I said that I extracted from this and the other codes what I believe that you need. In addition to these codes, also the ATC20 and ATC20-1 and the special design provisions for wind and seismic of 2015, and I showed you all these things, plus the masonry and the timber book, the masonry code, and the timber design book by Dr. Breyer, timber design book, the one I use it to teach this timber design class many times, and maybe some of you already took the course, so Remember this. Okay. So let us go to the business. So please, those of you who are taking or who enrolled in the class, don't forget the on-demand, and it is available for you. And if you have any technical difficulties or any technical problem, please let me know, and I will talk to my staff, or I will solve it myself if I can. So if we go to the 55 questions here, I will start with question number 55, and I'll go backward and I'll tell you why. Because there are some problems at the end here I need you to be aware of. Especially it needs a lot of calculations, and I need you to be familiar with these calculations. And after that, we'll go to the rest of the problems. And as I announced it last time, please, I hope that you get a chance to watch the recording of the 5 chapters, chapter 1 through chapter 5. So you can ask me any questions related to these 5 chapters. So the problem number 55 is asking, give you a drawing like this, and I sent this morning, so I hope that everybody get a chance to print it. The 4th level of the structure shown is located in the code. There are 3 important definitions I need you to be aware of, and these are listed in chapter 11, by the way, of the ASE 7, and I include them in my book. What is a base, and what is a level, and what is a story? Because when we calculate the seismic force, you might be asked about the seismic force at a specific level. When we talk about a drift is related to stories. So we need to know what is the definition for each, and we stick with these definitions even if you remember from school in other definitions. So the first one is the base. The base, and that's why we call V, which is a base shear, by the way. Base shear, or to be more specific, V is a seismic base shear. So what is the definition of a base? Where we V will be either coming from this direction or this direction is not the point. So the base is defined as it is the level at which the seismic force will be transmitted or imparted to the structure. It transmitted or imparted to the structure. So and this definition is given, I'll show it to you in just a minute. So it is the level at which the seismic force is imparted or transmitted. So when the ground start to shake under this structure, there is a seismic force will be transmitted or imparted to, or this in our case is going to be the base. But he's asking for the level. So the definition for the base, this is where the seismic force is imparted to or transmitted to the structure. This is the definition of the base. If you look to the level, I, as given in the code, level I is equal 1, which is level 1. Level 1. This is the first level. Level 1, is the first level above the base. Level 1. This is the first level above the base. So they call it level I, and after that they say I is equal 1. This is the first level above the base. A story is the space between levels. And the story X is the story below level X, by the way. So let us go to this illustration here, which I drew it to illustrate all these definitions. So we said that the level at which the seismic force will be transmitted or imparted to or moved to the structure, we call it the base, B-A-S-E, base. This, in fact, if you like to call the base is the level 0, I have no problem with that, level 0. This is level 1. And this is level 2. And this is level 3. And this is level 4. So the first level is level 1 is the first level above the base. Okay. What about story? Story is the space between levels. So this is the story 1. So story 1 is the one below level 1. You see, story X is equal below level X. This is the story 2. And this is the story 3. And this is the story 4. So we need to pay attention to these basic definitions. Even it looks simple, but when we start to come to the base shear V, and after that we are going to talk about distribution. Distribution means that I'm going to distribute this base shear into forces. We'll call it F1, F2, F3, and F4. We assign a force at each level. Assign a force at each level. So sometimes they ask you what is the force at level so and so. So in this case, we need to know what's the definition of the level and so on. So when we come to the chapter 6 and talk about the distribution of the force, seismic force, assuming that this is a given structure, and we do have the seismic base shear V has been determined, V, and we know V is equal C sub S times W. This is a seismic response coefficient. Seismic response coefficient. And we have some values for that, some equations. We'll see it later on. And W is the seismic dead load. Seismic dead load. So this V, we can distribute it among the levels as F1, F2, and F3. So this distribution is done according to an equation. We are going to see it. Distribution. And this is the force, or these are the forces at, this is level 1, and this is level 2, and this is level 3. Obviously, this also has the 3 stories. This is the story 1, and this is the story 2, and this is the story 3. And this is going to be the base, the base. So going back to the problem 55, sorry, I'm trying to put some information that we're going to talk about it in depth later on. So the fourth level is the first floor, second, third, or the roof. Obviously, level 4, the fourth level, is the roof. And this is the answer here. I'm sorry. So this is the answer for this one here. At the beginning of my book, you will find under glossaries and definition, or a glossary and definition, on page 51 of the textbook, you will find all these definitions, or the definition that I believe that you need, and I gather this from different sources, including the ASCE 7-11 chapter, ASCE 7-16, sorry, ASCE 16, chapter 11. Chapter 11, it does have definitions, and these definitions, the one we need to stick with it, because those are the definitions that will be accepted by the code, or this is what they agreed upon, and we're going to, and you will find all these things over there. Makes sense? Okay, so going to problem number 54. The plan view of the building shown below has 4 concrete shear walls and an AC unit. Here it is a plan view. This is a plan view, and this is a cross section. When you cut it, section CC. So this is a cross section. These are the walls, and we have an extension here. We call it a parapet. This extension here in chapter 7, we talked about non-structure component. So a parapet is a non-structure component. So dimensions are given. The wall has a parapet of 4 feet. Here it is. which is extension beyond the roof. And the parapet, as I told you, we classified as non-structural component. Non-structural component. And the non-structural component, or component, sorry, but this is a component. We cover them in chapter 7 of my book, which is based, this is the textbook, which is based on chapter 13 of the ASCE 7. And in fact, this is an architecture non-structural component, because non-structural components, they have two types, architecture and mechanical. And we are going to see this in chapter 7 one more time when we hit the problems related to chapter 7. This problem, in fact, is a little bit related to chapter 6, because asking what is the period of the structure, the period T. Or let me use uppercase T. T is the period in seconds, normally expressed in seconds. And the period is defined as a time for a complete cycle. For a complete cycle. Cycle of oscillation, obviously, complete a time required, or the time for a complete cycle of oscillation. So the period T is the time the period T is the time required for a complete cycle of oscillation. We're going to see an equation in chapter 4. T is equal to pi square root of W divided by K. Or if we know W, which is this weight, W is equal mg, mass time acceleration. So I can put this here as, or let me put it in terms of mass first. Okay. So it is mass over K, and I will define K in just a second. W is equal mg. From here we can say that the mass is equal W divided by G. So we can say that the period T is equal to pi square root of W divided by Kg. And again, if you have the book with you, very quick, if you have chapter 5, You will find this given, I believe, in chapter 5. Here it is. Equation 5 dash 2. When I have an equation like this is a period, the natural period of the building. What here it is a time for a complete cycle of oscillation of a single degree of freedom system. Two pi squared W over G times K, or in terms of M, where M is the mass, as indicated here. G is a gravity acceleration. Here it is, which is, as we know, this is 32.2 feet per second square, or 9.81 meter per second square. Again, these things, already I gave it to you. Do you remember the glossary and definition? I told you that. Here it is. You will find the G, for example, here it is, 9.81 or 9.8. This is centimeter. So the G is equal 9.81 meter per second square, or 9.80 if you like to call it that way. I have no problem with that. And 1 meter is equal 100 centimeters. So you multiply 9.81 will give you about 980. This is inch second square, which it came from the 32.2 times 12. So also I needed to be aware of this. So the G, which is 9.80 meter per second square, or 980 centimeter per second square. We need this, by the way. In chapter 6, we solve a problem. You will feel a problem that the G is required. There are some locations where the G is required, the gravity acceleration, or 32.2 feet per second square, or if you like to convert it to inches, so 32.2 times 12, this will give you inch second square. If you multiply 32.2 times 12, will give you the number. We just saw it together, which is 386.4 inch second square. So the period of the structure, T, is very important. So the T, and this is in physics, the period T is equal to pi squared M over K. K is stiffness. Stiffness is, by definition, is the force required to produce a unit displacement. A definition, K, and we remember this from school also, when we have the coil spring in physics, 4A or 4B or whatever the number, we determine the spring constant, we apply a force, P, and the spring will deform, delta, will be compressed. If we increase P, it will compress more. If we plot the relationship between B and delta, you will find this relationship is linear within the elastic range. The slope of this line is K. So K is equal B over delta. And here it is also in chapter 5. I just, okay, leave chapter 5 open at the same location. But I need you to study to a degree or to the level. Here it is, stiffness scale. It is on page 149 of the textbook. Page 149. Text. And the G I just talked about, here it is 32.2 or 386.4 inch or 9.81 meter per second square. If you'd like to add here, it is 981 or 980, whatever is. That depends how many decimal places. Centimeter per second square. So you have all the units here. So the spring stiffness K or the K stiffness K is the delta So I did not forget the problem number 54 yet. I am looking for the period. But he said that using the approximate method. Okay. At the beginning of chapter 6, we're going to see this. But let me just focus on one thing. This period here, as given in physics textbooks, for a single degree of freedom system, this for a single degree of freedom, which is normally you model our structures as we can to a single degree of freedom system. As you can see from this equation, T is equal to 2 pi, I know 2 pi, the square root of M over K. This is the mass, and this is the stiffness. In order to get the stiffness, I need the member sizes, how big these members of my building or my structure. In order to get the member size, this is a column, and this is a beam or a girder, and so on. And this is a connection between beams and or girders and columns. In order to get the period of the structure, I need its stiffness. But in order to get the stiffness, I need the member sizes. And in order to determine the member sizes, I need the period of the structure. And this is a joke, you probably heard it before, and I mentioned in the class, like the story of which one came first, the egg or the chicken. So is the period first or the stiffness first? So in order to resolve this issue, they came up with what is known as T sub A. T sub A. What's T sub A? T sub A, they call it in the quote approximate period. So they said, Mr. Mansour, you don't know the dimensions of the members that will be used for this building. And you need to design it. So we'll give you equation based on some, it is empirical formula or empirical equation as we call it. And we have 3 of them. 3 equations. The code developed these equations for us to help us to get the approximate period. This is what the A stands for, approximate. Until after that, I can revise my design to get the preliminary sizes, to get the mass, and get the stiffness, and do this is the exact. This is the exact solution. And there is a relationship between T and T sub A. We're going to see it in chapter 6. So one of the equation is C sub T H sub n to power x. And one equation is 0.1 n, where n the number of stories. And the first equation, the C sub T is a certain coefficient. H sub n is the height of the structure to level n above the base. H sub n to level n. And x and C sub T, they give us a table. And this table is given in the code. And I took the table and developed some values for you in order to facilitate or try to make it easy for you. But the third equation, this is the equation, by the way, they give it a number. It is in chapter 12 of the AS 12.8-8. And this is, the previous one, no, 0.7. And this is 12.8-8. And the third equation is T sub A is equal C sub Q, they introduced this the first time, over a square root of C sub W times H sub N. And they give us two values for C sub Q. C sub Q is equal to 0.0019 if we are dealing with feet, or C sub Q is equal 0.0058 if we are dealing with SI units. All this given in the code, and specifically if you look to my textbook on page 198, you'll find the first equation here. This is page 198. This is equation 12.87. And this is the table that has C sub T and X. And here are the other equations, the 0.1 n. And this is the little bit complicated equation, 12.8-9. And here are the values. And the C sub W is given by this equation. And I explain C sub W in a form of a diagram or a figure like this. And to the best of my knowledge, I am the only one who did that. Okay, or to the best of my knowledge. Maybe somebody else has a book talking about this, because this is a little bit tricky. And I don't know if I have some problems. I believe so. I believe I have some problems to explain what are these terminology, because it's not given in the. I need to check the new code. I was thinking to maybe in the commentary, since they came up with the new book, maybe they have some kind of illustration. But I read a paper way back, and I got the idea from a paper, by the way. I do not invent it. I cannot claim that. It's just a matter of illustrating the concept of the equation itself. So going back to the problem, and we should know when can we use this equation, C sub T H sub n to power x, when we can use 0.1 n, and when we can use this. Because there are certain requirements, and I will talk about it next time, okay? But this is just, okay, to solve the problem, but next time in chapter 6, we are going to talk about this. But for this specific problem here, the applicable equation here is T sub A, C sub T, H sub n to power x. This is the applicable equation. The other 2.1n and the lengthy equation, the C sub Q, this is not applicable, and you will see later on what are. So you need to select the appropriate equation. And the coefficient C sub T and X, H sub n is here, which is 12 feet. Not including the parapet. So this is a bearing wall system, concrete shear walls. This is concrete shear walls, which is a bearing wall system. Wall system. So when you go to the table that has the values of C sub T and X, as shown on page 198 of my textbook, you will find that we have one column for C sub T and one column for X. And the C sub T, you will find we have numbers here and numbers between parentheses like this. The number in the parentheses here, these are the metric equivalents. And here are 4 entries, 1, 2, 3, and 4. Here, moment resisting frame systems, which we don't have this one. We don't have it in our case, or this problem is not a, this is a building frame. This is bearing wall system. It's not a building, it's not a moment frame, it's not a building frame, it's not eccentrically braced frame, it's not steel buckling restrained braced frames. It's under other structures. So it is this and this. So in this case, if I come and plug these numbers, where I say that the C sub T is 0.02, and H sub n is 12 feet, and the X component is 0.75. If you do this calculation, you will get the period of the structure using the approximate method, which is 12 enter 0.75 and 0.02 times. I got 0.1289 seconds, which I can approximate as 0.13 seconds. And this is why I will select the answer C. I provided you with tables, by the way, to make it easy for you. And I will talk about the tables next time. And when we hit the tables, okay, in chapter 6, you will find that it could save a few minutes for you. Any question about this? So we need to know exactly what are the given information, what we are looking for to find what, and the most important, pick up the right equation. The right equation. Make sense? Good. I will be glad to scan these things and send it to you. I know my Egyptian handwriting. I don't know if you like it or, but at least it gives you an idea, okay, what I'm talking about. Okay, go to the previous page. Problem number 53. The plan view of a building shown below has 4 concrete shear walls So it is a bearing wall system, because as you know, in the seismic, we should know what system we are talking about, because we need to get the proper value of the R or C sub T, or so this is 3. So we call it lateral force resisting system. A lateral force resisting system. Lateral force resisting system. And the lateral force resisting system, this is the system that is responsible to take the seismic force, which is the lateral force, to bring it down to the foundation of the structure. This is a building or a structure in general. So I'm using a box like this. And there are some foundations here. Maybe it could be footings or maybe piles. It depends on the height of the building. This could be very long or could be just a footing. Whatever the number of stories of this structure. So basically, there is a seismic force. And this is a lateral force. We are going to see it later on, by the way, in chapter 9 and chapter 10 is like this. And you are going to see a problem just shortly about this, by the way. A lateral force at each level. It could be a distributed load or a concentrated load. Chapter 9 and 10, you will find a drawing like this. Maybe I need to get this seismic force, which is a lateral force. These are the seismic lateral force. Seismic lateral force. I needed to get it from its point of application all the way to go through the roof, for example, which we call it diaphragm. Take it all the way down, until it comes to the footings or the foundation in general, and go to the supporting soil. This is why we need to know the type of the soil very well. This is why they came up with the soil type A, and soil type B, and soil type C, and soil type D, and D default right now. They have 2 Ds. D based on testing, and D by default. If we assume it to be D, the code a little bit this time is a special requirement. And E and F. Those are the 6 types. A, B, C, D, E, F. A being the best soil. This is the best, which is hard rock. This is the best. And this is the worst soil. If the soil is bad, doesn't matter your foundation, how big your foundation is, because the supporting is really bad. This is why for soil type D and E and F, especially E and F, the code start to put a lot of requirements on the structure that's supported by a soil type E and F. This is hard rock, which is the best soil, hard rock. And we're going to see this also in chapter 6. But the point is, lateral force resisting system. So the lateral force resisting system, in order to help us, they came up with very nice way to describe this, and they broke it down, or I did broke it down according to them, according to the current code, a bearing wall system. Wall systems, let us make it plural. So means that the walls are responsible to carry the gravity load and the lateral load, because here we have a gravity load, by the way. We have load is coming, okay, down, which is the gravity load, but we don't design for it. We are not concerned about the gravity load in this course. So we have a gravity load and we have a lateral force or lateral load. Lateral load. We are concerned about this here, which is the earthquake force, not the wind load. This is the E is the earthquake force. Earthquake lateral force. Earthquake lateral force. So the first one is a bearing wall system, or the bearing wall systems. The second one is building frame systems. Frame systems. And the following one is the moment frames. Moment frames. And we could have a hybrid of this. Let me make it the fourth one, which we'll call it a dual system. So the dual system is a system that consists of a combination, and we're going to see it. It's called dual system. So basically, you can break it down the lateral force resisting systems into bearing wall systems, building frame systems, the moment frames, and the combination, which number 4, they call it dual systems. And they have a very big table, which is the largest table in the code. I put it in my chapter 6, table 12.2-1. This here, you will find there is a table in the ASCE, table 12.2-1. This is a table 12.2-1, yes. This is the largest table or the biggest table. It does have all these systems, and they broke it down into subsystems, about 83 systems. It does have 83 systems, if I count them correctly, I believe. But you have it and you can count them. Let me know if 83 systems. And on the exam, you need to know what exactly, which system they are talking about, because there are some values we are going to get from this table. We can get the R, we can get the omega sub O, and we can get what is known as the C sub D, deflection amplification factor, and R, the response modification coefficient, and omega sub O is the omega sub O. Let me see, I forgot. Over strength factor, what it is. Over strength factors, forgive me, team. I didn't sleep very well last night, so this is the over strength factor. Over strength factor, this deflection amplification factor, amplification factor, and the R, response modification coefficient. Response coefficient. So in order to get the probable value of R, omega sub O and C sub D, you have to know which system he's talking about. And this is a table 12.2-1. I keep the table number as is, because any table I take it from a code or equation, I try to keep the original table number and the equation number so you can refer to it. Make sense? Okay. So sorry, I'm trying to explain the things that is related to the problem, and we will. So this is the bearing wall system. Bearing wall system. As you can see, walls, this vertical wall, and this is the roof or the diaphragm. And these walls are responsible to carry the gravity load and the lateral load. This is the parapet we talked about. The unit weight of the roof are given to be 45 and 60 pounds per square foot. And the AC unit, it's 2.5 tons. We have an AC unit here. The relative rigidity of all walls are shown. And all walls have the same thickness, which is 5 inches. And the seismic design category C. And the SDS is 0.7 G. And the unit weight of the concrete, unit weight, unit of concrete, this what they meant unit weight, by the way. If you would like to, I know it's understandable. Unit weight of concrete is, which is gamma concrete. And the question is, what are the X and Y coordinates of the center of mass of this building? We have coordinate system X and Y. So this is the origin here. This is O. He has to give you the reference. He has to give you the reference. So he's asking what the center of mass is somewhere. It is somewhere here. This is a plan view. The center of mass is somewhere here. CM. He's asking for this dimension from here to here, which we'll call it YCM. And this distance from here to here, which is XCM. And we need to know the center of mass, because this is where the seismic force will go through. The base shear V, it goes through the center of mass. And as you can see from the 4 answers, he is so tricky. I put it that way back 25 years ago, when I was teaching seismic here at CSU Fresno. Remember that. You'll find this dimension is 50 feet. The Y sub C, by the way, due to symmetry, is 25 feet. But to put all of them 25 feet. He put all the Y, here it is the X and Y. The order, by the way, is very important. So the first number is the X, and the second number is the Y. We need to be careful. Sometimes they use the northern and the eastern. So he will tell you, okay, here it is. This is the northern direction, and this is the eastern direction. and the center of mass will be somewhere here for whatever structure is. So he can give you the coordinates of the center of mass based on the northern and the eastern. Here he go put it x and y because he give me x and y. So pay attention. This is it. Also, I have some problems, I believe, or I saw some problems, or it could be this way. If no, I use the northern and the eastern also. Yes, I used it. Yes. So we need to determine the CM, the center of mass. Where is center of mass? So I cannot really, by the process of elimination, I cannot eliminate any of these because all of them 25, 25, 25, 25. That means that he is forcing me to calculate the value of x, C sub m, x of the center of mass. If I'm able to get x, for sure I will pick the right answer. Make sense? Okay, let us take a short break, about 10 minutes. I need to wash my face and come back. Try to also get some fresh air. I was joking with every engineer or during that time. Forgive me for joking, but try to keep your spirit as high as I can, including my spirit too, because of this coronavirus. So I always say, okay, well, please get fresh air without any coronavirus, please. And we need just fresh air, the pure fresh air, the pure fresh air. Okay. So let's take about 10 minutes from now, so I can wash my face and walk around a little bit to wake up, because I told you I didn't sleep very well last night. I was so tired this morning and this afternoon also, but I will keep working with you guys all the way. And I did this morning also. I work all the way until about 11:45, I believe, or 11:40. So let's take a few minutes break, 10 minutes break, and come back. It's about 2:17 right now. So let's come back at 2:30, okay, and we'll continue our discussion. Thank you very much. Okay, welcome back, everybody. So the center of mass and the center of rigidity calculations. But before I start to calculate that, I need to pay your attention that at the beginning of the book, the textbook, I put a concise and comprehensive summary. At the beginning of the book, you will find that a concise and comprehensive summary. And this summary broken down into code equations and non-code equations. So on page 7, for example, of this summary, I hope that all of you there, summary of code equations, like the equation I wrote today that V is equal C sub S times W. I give the name of the equation. And when can we use it? And what are the parameters needed for this equation? And so on. And after I finished the summary of the code equations, I entered another table or constructed another table, which I call it table 2 on page 13. I call it summary of non-code equations. For example, the center of mass and the center of rigidity is among those non-code equations because they are expecting that we will know how to determine that. Here it is. This equation 22 and equation 23 for the center of mass and the center of rigidity. So nobody will ask you to memorize equations, but we need to know where they are located and when we can use them and what are the parameters. So I have XCR for the center of rigidity, YCR for the center of rigidity, and XCM, the one we are going to use right now, and YCM. In our case, YCM is by inspection is 25 feet because it is due to symmetry. And I will explain this one more time. So these are the equations that I need you to be aware of, where they are located and how can we use them. So what is the story of the center of mass and the center of rigidity? Center of mass and center of rigidity are extremely important as far as their location or the determination of the center of mass and the center of rigidity, because if you look to any building, a plan view like our building, let me, for the sample problem here, you will find that we do have a wall here, and there is another wall here. Let me make it a little bit bigger here. And we have another wall here. And we have AC unit here. And we do have another wall here, which is a short wall. And the rest are openings. And this is what you see here, but I draw a little bit bigger. So I said that the center of mass is somewhere here. And he defined that this is X and this is Y. And this dimension is 50 feet. So due to symmetry, the center of mass is halfway of the 50 feet. Because he said that from here to here is 25 feet, as indicated here, from to the center of the AC unit. And this is 30 feet only. And this one here is also 30 feet. Sorry, my drawing is a little bit 30 feet, 30 feet. I can make this a little bit shorter, at least to balance it a little bit. It is. And this is 60 feet. Let me get another, for some reason. Here it is, 30 feet. And we define this parameter here as YCM, and this parameter from here to here is XCM. And we said this by inspection is 25 feet. So if I'm getting or calculate the C sub XCM, I will be able to pick the correct answer. So the center of mass and the center of rigidity calculations, as I explained in chapter 3, by the way. So the centroid for an area, centroid for an area, which is sometimes we call it Y bar, is equal the sum of the AI YI over the sum of the AI. And I have a problem in chapter 3. It's talking about the centroid for an area. When I have a T-beam in chapter 3, one of the sample problems, and we were able to determine where is the centroid using this equation. So the centroid, where the axis, with centroidal axis, C. What they did, we took the same equation to calculate the center of mass location. Center of mass and the center of rigidity, which is CM, and the center of rigidity, CR, center of mass and the center of rigidity, center of mass and center based on these two. These two based on this, or these two based on this equation. But when we're talking about area, we use A. When we are using the center of mass, or determine center of mass, we are using M. When we calculate center of rigidity, we are using R. So for this problem here, the XCM, based on the equation I showed to you, which is equation number 23, XCM, it is in parallel to this, is the sum of the MI XI over the sum of the MI. And this is the equation 23. Obviously, I give it a number because there is no equivalent equation in the code. So this is equation number 23 on page 16 textbook. So far, so good. Let us do the math. And I'm sure that you are going to have some questions after we finish, but this is the purpose of this exercise. The biggest problem with the center of mass calculations, you may forget one of the masses. You may. But when we calculate the center of mass, if you remember the 7 rules, do you remember the 7 rules in chapter 7 and chapter 5 and when we calculate the center of mass, here we are using all masses should be used to determine the location of center of mass. But the center of rigidity, no. Not all the wall. Not all the walls, as we are going to see shortly. Certain walls, not all the walls will be part of the center of rigidity calculations. Sometimes in certain configuration, all walls, but not necessarily. But this is a rule, always. So what do we have? We have the roof. So I will take each mass multiplied by its distance, where xi is the distance from the centroid of the element to the y-axis. So I will do the first one is, and let me put it here. In a problem like that, I know it is very lengthy, but I don't know if they can ask you this or not on the exam. Maybe a little bit more simplified one, but I will count them. I have one wall here, or let me, the roof. It is one mass. I have one wall, 1, 2, 3, 4. I have 4 walls. I have the AC unit. So a total of 1 plus 4 is 5. 5 and AC is 6. So 6 components must be shown here. If I miss one, that means that I did something wrong. Are you ready? Let's start with the roof. The roof is 90 by 50. This is the surface area. It is 90 by 50. How thick it is, the roof? He told you the roof is, I give the roof directly. The roof, okay, has a weight of 40 pounds, 45 pounds per square foot. So it is 45 pounds per square foot. So the square foot 90 by 50 will give you the surface area time the unit weight. This is the mass by itself. But the roof has a centroid, which is this 90. So the centroid of the roof is halfway, which is 45 and 45. So I will multiply this. This is the xi, which is 45 feet. So far, so good. A plus. So I finished 1 out of 7. Out of 6, sorry. I will take this wall. This wall, it does have a 30 feet wide. And this is also, I can make 50 feet times. The height is 12 feet. So this is the surface area. Time, the unit weight for the wall is 60 pound. And he said that 60 pound per square foot. How far from the centroid of the wall to my reference axis here is 90 feet. I finished the wall number 1. So I would say plus. And the roof, plus. A plus. For 1 wall. These 2 walls are symmetrical, by the way, or they are the same. I can say 2 walls times 30 feet times 12 feet times 60. How far from the centroid of this wall to this here is 15 feet. And I multiplied by 2. That means that I have 1 and 2 walls here. So this wall is done and this wall is done. I will hit the AC unit. It is 2.5 tons. So it is 2.5 times 2,000 pounds per ton, times the distance from here, from the centroid of the AC to the y-axis, which is 15 feet, is given. Is given as a 15. So I am done with the AC. I put the numerator. You can add the denominator immediately, by the way, because the denominator is a mass. So you can say this is 90 times 50 times 45. This is mass number 1, a plus. I have 30 times 12 times 60. A plus. 2 walls, 30 times 12 times 60. A plus. 2.5 tons times 2,000 pounds per ton. 1 wall to go, which is this wall here, which is 50 feet. Sorry, the numerator here, I can say, I will continue like this. So I will say a plus here. It is 50 feet times, the height here is 16 because the parapet, times the unit weight, which is 45. Sorry, no, 60. The 45 was for the roof. So 60. Which is this one here. Multiplied by how much? Multiplied by 0. But don't forget to put it in the denominator. Even multiplied by 0, but still by 60. So I have 1, 2, and 2 is 4, 5, 6. Bingo. I have 6 units here. 6 elements. Did I miss anything? The answer is no. To the best of my knowledge, unless you can. If we do this math, let's do it together. If you are faster than me, that's good news. Because you are younger than me, you're supposed to be faster than me. So it is 90, enter, I hope that you can read my Egyptian handwriting. Let me get closer here. Here we go. At least you can see the 90, enter, 50 times, 45 times, and also 45 times. So, and 30, enter, 12 times, 60 times, 90 times, 2, enter, 30 times, 30 times, 12 times, 60 times, 15 times, and 2.5, enter, 2000 times, and 15 times, and finally 50, 16 times, 60 times, 0 times, obviously. So in this case, I know it is time consuming and you might do a mistake easily. So I got, hopefully my math is correct. And let us see if I did a mistake. Let's get the math down. The math here is 90, enter, 50 times, 45 times. So this is 32033. So enter here, enter, and 30571 500 times. I did a mistake somewhere. This number, it seems to be a little bit bigger than what. Let me do it one more time. Okay. I have the solution. I can show it to you what it is, because what I needed to do it with you, at least you can this number most likely is wrong. Let me do it one more time, probably. I get this number here, 11,779,500. So if you do this, 320, 300, divided, I got 36.78 feet. I hope that you agree with me. Anybody got the same number? 36? I need either yes or no. Anybody can support me or correct me. Unless if you are doing the calculations. Let me, I believe, as I said that I have the something similar to this problem somewhere here. Just to confirm. $66. Okay. Anybody got the same answer? Anybody support this number so far? And this is the correct number, by the way. 36.78, yes. And if you have the 6 to 6, if you have the 6 to 6 with you, because I took this problem from there, if you go 6 to 6 book, and if you go to problem number 22, number 22, you will find this number there. And this is what I was verifying. And instead of showing you the solution, we did it together. But do you understand? Okay, so right now, I can go back right now and mark my answer, because right now I narrow down my answer to answer D as in doctor, which is this one here. So the center of mass, and I have many problems, you will find that the mistakes that we might do, we don't probably do the math right. I did it the first one, it came a number, it does not make any sense. And after that, I did it again next time, it turned out to be correct. Don't forget that some members will be multiplied by 0. Don't forget the count the number of elements. Don't forget that the all masses will be part of. Make sense? Okay, so this is a problem number 53. Sorry, it took long, but at least we understand. And if you have the center of mass calculation, try to be careful, as I told you, the common mistakes. That we do, and forgetting one of the wall, do the math. Don't take the right density or the right unit weight. And as I told you, if you go to the 626 problem number 22, you will find a problem similar to this. And the same problem was given, but is asking for the center of rigidity. This is an easy one. And also is asking you for the coordinates for the center of rigidity, the two coordinates, x and y. So the center of rigidity is somewhere. This is rigidity 8 and this rigidity 8 are 8. So he gave you the relative rigidities. And this is 12. So the center of rigidity is somewhere here. Before I leave the center of mass, as you can see, the distance 36.78, the one we got, here it is. This is the distance. So the center of mass, the whole distance is 90 feet, as you can see from here. The center of mass is closer to the concentration of the mass. You see the distance from here to here is only 36.78, more than 1/3 of the entire distance, because we have an AC unit here, we have a wall here, we have a wall here, we have a wall here, but we have an individual wall far away from the concentration of the mass. This is why the center of mass is closer to the concentration of the mass. Center of mass is always, and this is true also for the centroid for an area. When I cover this, I explain, I said that if the area is changed, this is the flange, and this is the web. If the area of the flange increased, the centroid will go up, will move. It will get closer to the concentration of the area. And this is true for the concentration of the mass and the concentration of the rigidities. And this is why if you look to this problem here, problem number 52, I have the relative rigidities. He gave it to me. Sometimes he did not give you the relative rigidity. You have to use H over D ratio, the one we use in chapter 5, H over D. And you need to decide if the rigidity is cantilever or rigidity is fixed. So I have 8 here and 8 here, and 12 and 7. So due to symmetry, I'm expecting the center of rigidity, which is CR, to be from here to here is from here to here, halfway between this wall and this wall, because the center of rigidity will go up and down in relation to this, the relative rigidity of these two walls only, and moves right or left in relation to the rigidity of this wall and this wall. In fact, it will be closer to this wall than this wall. So for sure, this YCR, it must be 25 feet, which is half of this. So I can get rid of this and get rid of this. Here he is nice. Due to symmetry, this is because of the symmetry. Always look for symmetrical situations. So what I need right now, I need to get the X center of rigidity. And this is very easy, one simple equation. I will some moment about the Y, or I can say that the XCR is equal what? Here, not all the walls. Center of mass, we use all the walls and the AC. Here, certain walls. This wall and this wall only. The other walls will not participate in determining the center of rigidity location in the X direction. So I say that this is 12 times 0, because I'm summing moment here, divided by 12, because the center of rigidity here is the sum of the Ri xi divided by the sum of the Ri. Here I'm using rigidity. I replace the letter A for area with mass, if I'm talking about mass, with letter R if I'm talking about rigidity. A plus. This here is 7 times the distance from here to here, which is 19, divided by 7. That's it. The other two walls have nothing to do with that. So this is 19, and this is 7 times 90 is 63. So if you do this math, I got 33.15. Bingo, here it is. The answer is B. So on the exam, if you are getting close, you have only 1 minute left, and you have a situation like this, and he give you a lengthy discussion about, or lengthy information, and is asking about the coordinates. Sometimes they ask only for one coordinate, by the way. Sometimes they ask for two coordinates. Be careful what they are asking for. They might ask for one coordinate, and sometimes they ask for two coordinates. So if by the process of elimination, I can eliminate answer C and D, as I told you, due to symmetry. Please remember this word, symmetry. Let me write it down here, so when you get my notes, symmetry. For the center of mass and the center of rigidity. If there is any symmetrical certain number of walls, I try to get the benefit of this property. So I have two answers left. Both of them are 25, because I know it's 25. And I have 44.15 and 33.15. And you have only 30 seconds or 1 minute, and you don't, this calculation shouldn't take more than a minute or so, assuming that you remember the equation. And where is the equation? but at least you 50-50, or you can proportion 12 with respect to 7. Okay, so this is the way also we do it, that 12 over 19, in fact, and 90 times, but you need the opposite one, so it is 90 minus. Yeah, I got a 33.15. So you can proportion that. Proportion so the center of rigidity is closer to the concentration of the rigidity, because, or the walls with higher rigidity. This is 12 and this is only 7. Because this 8 and 8, so it is halfway. Okay, bingo, easy stuff. Everybody with me, or you are thinking about the stock market tomorrow? Is the stock market will go up or down? Or you are thinking about Corona, what will happen to tomorrow about, I hope that. Number 51. Let me give you a chance to read it. Give you 2 minutes. And I will do all my best in the future to send you the problems early. I'm really, really busy, but I'm doing all my best. But I will do all my best to send it as early as I can, because I needed to sit 2.5 hours and work all these problems. Even if you know the solution is given somewhere, I will do it on my own. I will solve these problems as if the first time I see it. Let me give you, each problem is 2.67 minutes or 2.7 minutes. Let me round it. Minute, because they give you 55 questions in 2.5 hours, and this is the biggest problem. So it is 150 divided by 55 is 2.7. 2.7. I was wrong here. 2.7. 2.72. 3 minutes. Let me give you 3 minutes from now. So 3:14. So 3:17. Okay. So the given problem is talking about the distribution of the force, the seismic force, among the vertical columns or vertical piers. So I have this force here is given 160 kips. And you have a column 1, column 2, column 3, and this is slab, rigid concrete bridge slab. And the word rigid is very important. When the connection between the superstructure and the column rigid, we consider this is a fixed. So the word rigid, I need you to say that the moment that word rigid is mentioned, mean this is fixed. So the top, me. Sorry, I went to get something very quick too. So the moment that you see in a problem statement that the connection between the slab or the roof and the wall or the vertical column, whatever system is given, immediately I will think about this fixed. He said that 3 columns are shown made of concrete and the most of elasticity is given E sub C. Concrete, as you know, the most of elasticity for concrete E sub C is about between 2 to 4 or 5 million psi. This is different from E steel. As you know, the most of elasticity for steel, E steel, the most of elasticity E. This is most of elasticity, not the earthquake force. E steel, we are using letter E also, is 29 million psi, as you know, or 200 GPa. For E concrete, the most of elasticity, this is, by the way, one number for all kinds of steel. E concrete, the concrete modulus of elasticity E is not constant like steel. Varies between maybe 2 to 4 or even 5 million psi, because it depends on the strength of the concrete. And he will give it to you. Normally, such a property must be given to you. So he gave it to you here as 3.6 million psi. The moment of inertia is given, I. Columns 2 and 3 are fixed top and bottom. Here it is, rigid concrete. So this column is fixed top and fixed bottom. This fixed top and bottom. But column number 1, it is assumed to be bent at the bottom because of a soft soil. So this column number 1, we can make it is fixed top and it is a bend at the bottom. This is number 1. So he's asking the resisting force for column number 2 is what? We know one of the 7 rules is a seismic lateral force will be distributed among the resisting elements in proportion to their rigidities or stiffnesses. So in this case, I have a force, I will call it F1 for column number 1, and I will call F2 and I will call this is F3. F1 plus F2 plus F3 must equal 160 because equilibrium still sigma force X equals 0 and sigma force Y equals 0 must satisfied or must be satisfied. So how can we get F1, F2, F3? So let me write it down here. F1 is equal to this force here, which I will call it P or call it F. If you like to call it also F, I have no problem. Here it is F is equal F, which is the total seismic lateral force, times, I will call the stiffness for this one is K1, and I will call the stiffness, this is K2, and the stiffness is K3, times K1 divided by K1 plus K2 plus K3. Why I am adding them? Because this is a parallel system. Do you remember the parallel system? So these three columns is a parallel system. Parallel system. Where the total K total, or K equivalent as we call it, is equal what? Is equal K1 plus K2 plus K3. And this is here it is. So this is the K total or K equivalent. So far so good. How can we get K1 and K2 and K3? Again, this will go to chapter 5. At the end of chapter 5, there is a table. It does show the stiffness for different end conditions. Let me bring the book here, and all of you know where is the table or which table I'm talking about at the end of chapter 5. And you promise me that all these pages and all these things will be stored in your brain, chapter 5. And this is the table I'm referring to, which we used it before we solve a problem. This table here before the tables of the H over D ratio. This is the table shown on page table 5-3 on page 154, please. And this table gives you the the stiffnesses and the deflection from structure analysis. Nobody will ask you to derive these equations. Stiffnesses, if the column is fixed, we are using 12 EI over H cubed. If the column is fixed hinge, we are using 3 EI over H cubed. If the column is fixed free, we are using 3 EI over H cubed. And the other one, which is the brace system, I included also. And as I mentioned before, this was in the past. Dr. Chopra, he's a professor at UC Berkeley. He's a professor of civil engineering. He has a book. And at one point of time, the board considered or adopted his book. It was a little bit complicated book. I used it twice when I was teaching structural dynamics here at CSU Fresno. And I kept it just in case if they ask you about a brace system, how to get the stiffness of the brace system. It is EA over L cosine square theta, and I define the parameters for you. But in our case, we are going to use the 12 EI and 3 EI. So in this case, we can solve it together when I say that K1 is equal, this is the 3 EI. 3 EI over H cubed and K2 is equal K3, and we are lucky that all of them have the same height, but I have another problem. They will find the height is different. So K2 and K3 is 12 EI over H cubed. So basically, I can say that I need F2. So F2 is equal the total force times K2 divided by the K total, which is K1 plus K2 plus K3. So here it is. I can put it. Okay, so this is 160 kips. I don't have to calculate, by the way. I can. K2 is equal what? Is equal to 12 EI over H cubed divided by K1 plus K2 plus K3. So it is 3 EI over H cubed plus 12 EI over H cubed plus another 12 EI over H cubed. You don't have to substitute for the numbers because the numbers are getting really big. They give you the numbers just, okay. But I can factor EI over H cubed out, and this will cancel with, so it is 12, here 12, and the 3, and the 3, and 12, and 12. So you can say this is, unless I did something here different, no, it's still the same. So in this case, it is 160 times 12 divided 12 and 12, so it's 27. And this here, the number hopefully is among the 4 answers. So it is 160. Did I do something wrong here? No, that's correct. 12, 27 divided. I got 7111, 71.1 kips. And this is the answer D. You see that? I don't like you to go and do the calculations and put 3.6 million and 140 million and all these things, and they turn out, oh my God, I can factor these things out. So we need to reduce our computations or our math, because every time you do computations or calculations like the problem we solve it together, the center of mass, you see that it is easy to do a mistake or make sense. Any question about this? And this is the way we do it, and let us do our best in order to get the maximum number of problems. Okay. Now you are, any question about problem number 51? Problem number 50. This is asking for the X and Y coordinates for the center of rigidity. The center of rigidity is somewhere here. And again, he is asking for two coordinates, which the X and Y. This is YCR, and from here to here is the XCR. Here we have two walls, A and B. They are not perpendicular walls. This non-parallel system. The problem that was solved before, it was a parallel system. Center of mass and center of rigidity was straightforward. Here, in calculating the center of mass and the center of rigidity, these two walls, be careful, they are going to be contributing to both directions because they are not parallel system. But this wall here, it will only contribute the location in this direction. This wall is going to contribute in the Y direction only. And that's why when we are saying this, the 7 rules, I needed to review them again. They are given in chapter 5. And I put them in chapter 6 also in my book, chapter 5. Just immediately before, I believe, before the table they were looking for. Here we go. The 7 rules. This is on page, by the way, 153. The 7 rules at a glance. The seismic base shear acts at the center of mass always. The resultant of the resisting elements R acts at the center of rigidity. And all masses will be used to calculate the center of mass. Do you remember the center? We use all masses, all walls and the roof and the AC unit, all masses that part of the building is going to be part of the equation or contributing to the equation. Here, certain, not necessarily all rigidities or stiffness will be used to calculate the center of rigidity. I need you to be aware of that. Here it is. This is the rule number 4. And rule number 5, the seismic force is distributed among the resisting elements in a proportion to their rigidities or stiffness. If the diaphragm is rigid, exactly like what we did here. For this problem number 51, this seismic force is distributed among these vertical columns in a proportion to their stiffnesses. Here it is. And again, remember that don't put these fancy numbers or the big numbers that they give it you. Oh, sorry. So the 7 rules here, please, from time to time. And number 6, the seismic force is distributed among the resisting elements in proportion to their tributary area if the diaphragm is flexible. And rule number 7, the seismic shear is resisted by certain, not necessarily all walls, but the torsional moment is resisted by all walls. Do you remember M sub T? Which is M sub T A, M sub T, the inherent, plus the M sub T A, which is accidental. The total torsional moment is equal the inherent torsional moment plus the accidental torsional moment. So the torsional moment is resisted by all walls, but the direct shear, no. Direct shear not necessarily is resisted only by the parallel wall system. If they are parallel wall system, certain walls, not necessarily all walls. So if you look to this for non-parallel system here, we need to determine the center of mass and the center of rigidity. The center of rigidity only. The center of rigidity, I don't know, the center of, coordinate center of or rigidity. Or this, I believe this is an extra or here. I don't know what is this. R, center of, the coordinates of center of rigidity, this of. Sorry, here it is, typo. Let me give you 3 minutes and do it. I'm sure that you can do it, because already I talked a lot about the center of mass and the center of rigidity. You have the equations, equation 22 and 23. And be careful because we have a slanted wall here and a slanted wall here, or non-parallel wall here and non-parallel wall here. So we have to consider these walls when we calculate the center of mass or the center of rigidity. But in this case, the center of rigidity. So 3 minutes from now, what about that? It's 3:41, 3:44. Okay. And he gave you the relative rigidities for each wall. And as I told you, if the R, as I told you, the R is used twice. in this code, not twice, 3 times. Okay, so the R we use it as center of R is for rigidity, for shear walls, and the R is equal 1 over deflection, by the way, as you know. The second R we use it, the one I was talking about in table 12.2-1, which is the response modification coefficient. R is the response modification coefficient, that's correct. Okay, just to make sure, response modification coefficient, that's correct. So response modification coefficient. Okay, this is the one we are getting from 2 tables, by the way. Table 12.2-1 and the table 12.14-1. These 2 tables in chapter 6, I'm going to remind you with. This is for the ELF, the equivalent lateral force procedure, and this is for the simplified method or the alternate design method. Alternate method. This is where we get the R, but we call it R. And there is another R, but it is R sub B. The code is called response modification factor. Response modification factor. And this is in chapter 13, 13.51 and 13.61. This is for the non-structure components. So there are 3 R's in this code. R is the rigidity for the shear wall, which is basically the resistance to deflection. This is a shear wall, and we talked about this, how to get the R, and we use H over D ratio. And the tables are provided in chapter 5 of my book, chapter 5 of the textbook. So far, so good. Just I'm trying to throw everything. And do you remember ELF? Equivalent lateral force procedure. This is an alternate method, or sometimes we call it simplified method. And this is the equivalent lateral force procedure. Equivalent, EQU, equivalent lateral force procedure. Okay, so here the R is given as the rigidity, the relative rigidities of the wall. And we use relative rigidities because we are distributing the force, the seismic force in a proportion. So everybody got it? Answer, which answer? Problem number 50. 5-0. The equations are still the same, by the way. The YCR is equal the sum of the RI, YI over the sum of the RI. The XCR, and by practice you'll remember all these equations. It is the sum of the Ri Xi divided by the sum of the Ri. Those are the two equations to get the YCR and XCR. Okay, this off here, please correct it, and I will correct it, and let's do it together. Unless somebody can give me what answer did he get. I need an answer. Are you done? At least I know that all of you are thinking with me. You are not thinking about the stock market tomorrow. Stock market will be fine, don't worry. Okay, let's do it very quick. So the YCR is equal to, this wall has nothing to do with the, no, it does, not X. This wall, yes, it does. So I'm summing moment here. So this wall is 6 times 0, divided by 6, a plus. This wall, okay, for YCR is 2 times what? Does this wall here perpendicular to this has anything to do with that? No. This wall, it does not control, the center of rigidity will move this way in the proportion to this rigidity and this rigidity and this rigidity. The center of rigidity going up and down in the proportion to this and this and this. So this wall has nothing to do with the location of the center of rigidity in this direction, but in this direction. So I look to this wall 2 here. From here to here, how much is that? This is 30 feet, and this is 30 feet. The centroid of the wall in the middle. Okay? That means that this distance from here to here is what? Is 15 feet. Remember that? Okay? This is half of this. Because this in the middle, the centroid. That 15, what is left is 15, so 2 times 45. And I add 2 at the bottom, a plus. The same story, this for 3. And again, the 3, the centroid is here, so the distance from here to here is 30 plus 15 is 45 times 45, and this is divided by 3. So in this case, if you do this calculation, 2 times 6 times 0, and 2 enter 45 times, and the 3 enter 45 times plus, divided by 11, I got 20.45. 20.45 feet for the Y. As you can see here, for the Y, in the same order, by the way, be careful with the order. This is 20.5, and this 20.5. So I will exclude these two answers here. So I have 60 and 62.1. So this will C sub CR that now I'm summing moment about here. So this wall, yes, 2 times the whole distance, which is 90 feet, divided by 2, plus the same here for this 2, multiplied by 15, plus 3, let me add 2 here also, plus 3 times, this is 15 from 90, so it is 75 divided by 3. If you do this math, 2 times 90 plus 12 times 15 plus 3 times 75 divided by 7, this will give you a number. Let us do it. So 2 enter 90 times, 2 enter 15 times plus, 3 enter 75 times plus, 7 divided, I got 62.14 feet, which is basically the answer D as in doctor. So when we are talking about the center of mass and the center of rigidity, so whatever the building is, so the center of mass and the center of rigidity, center of mass and center of rigidity and the center of rigidity. It seems to me when you don't have enough sleep, you are getting things. Center of mass, center of rigidity. So we have parallel system and non-parallel system. The center of mass, it doesn't matter. It is parallel or not parallel. The center of mass, all walls, or all masses, sorry, masses, because the roof and the AC, so all masses, irrespective. But for the center of rigidity, for a parallel system, certain walls, for the center of rigidity. And for the non-parallel system, also we could have certain walls, not all walls, certain walls for the center of rigidity determination. I need you to pay attention to this. When you have a parallel system like this, I have a wall here, and I have another wall here, and I have a wall here, and I have a wall here, So when I set my coordinate system, X and Y, and this is the center of rigidity, and this is the YCR, and this is the XCR. Okay, when we have non-parallel system like the situation we just solved, have a wall like this and a wall like this, have a wall like this, have a wall like this, and this is X and this is Y, or a non-parallel system also. I believe I have another problem somewhere. This wall this way, and this wall this way, and this wall this way, and this wall this way. Okay, so he give you like a very strange building. Okay, where something like that. This also is a non-parallel system, but in this case, all the walls right now, so X and Y. I needed to be ready for that because right now we look to the center of each wall like we did here. If you applied here, for this one to be here, so I believe I have a problem somewhere similar to this. But this is, so I need you to be aware of that. Make sense? Okay, good, good. Everybody is awake. Let us look to the previous. Problem number 49. This is the load deflection curve. This is P, and this is delta, like the one I use it for the spring stiffness illustration. And he is giving you 4 walls, 1 through 4 were tested under static loads up to failure, and the corresponding load deflection curves were generated as shown. So it's asking which wall has the largest rigidity. Rigidity R is 1 over delta. Who said that? This is in chapter 5. Can you go to chapter 5? Let me get it here. So the rigidity is the inverse of the, let me other I'm looking for. Here it is. That on page 152 of the textbook, the R for the cantilever, assuming that the wall is fixed from one end and free from the other end, we call it RC, is 1 over delta C. So the larger the deflection, the smaller the rigidity. So they are inverse proportion. This is large, this will get small. But if this is getting smaller, this is getting larger. Do you see that? We need to be aware of that. The relationship between rigidity and deflection, because so based on this, I'm looking for something for the problem I was telling you about the 4 walls that they are inclined, but that's fine. I will look at it later on. So going back to this problem here. So I needed to be aware of that. The concept is very, very important. So this is, as this gets smaller, this is get larger. So either wall 1 or wall 2 or wall 3. 1, 2, 3, 4, sorry. Okay, what's the answer? This here, it has a smaller deflection here. Wall number 1. Any question about that? Agree or disagree? Largest rigidity. More rigid. Rigidity. You see the deflection here for wall number 2? Huge deflection. For number 4, huge deflection. This is the smallest deflection. And it has the steepest slope, by the way. The modulus of elasticity, if you remember, for concrete and steel, this is just something, an analogy, that the sigma times epsilon, sigma epsilon, if this is a modulus of elasticity, or this is the slope of the linear portion of the stress strain curve for steel, steel, you will find that the corresponding curve for concrete is somewhere here for E sub C, because steel is more rigid than, okay? So I need you to be aware of that. So rigidity is the reciprocal of deflection, and obviously the and look to see how much load, the peak load here, in order to produce this deflection here, which is at the ultimate load. Here they carry less load, okay, and they produce a large deflection. Let me grab a question from one of you, or a correction, or clarification, or disagreement. Wall 1, oh, you are telling me the answer. Thank you very much. I thought this is disagreement. What about problem number 48, which is the same, but he's asking which one has the largest ductility or the highest ductility. Ductility is the ability of the material to absorb energy. And ductility is basically the area under the stress strain curve up to failure, which we call it modulus of toughness. Do you remember toughness? Toughness. So the ductility is related to energy that can be absorbed. That can be absorbed, which is the total area under the stress strain curve. Stress strain or load deflection, by the way. Strain or load deflection curve. Which we call it toughness. which is basically the area. If you look to the area, if you look to wall number 2, let me get a marker here. Wall number 2, if you look to the area under the stress strain curve or the load deflection curve for wall number 2, this is a measure for ductility. So if you compare this area with all other areas under the same load deflection curve, this for number 4, for example, or number 3, or number 1, obviously for wall number 2 is the highest. And this is why for this problem number 48, the answer is wall number 2, which is answer B. Any question about that? Good, okay. If you look to the other problems, this is problem number 46. What about if we take about 5 minutes break only, just to stretch your back and come back after 5 minutes? Please to stretch our back a little bit. Thank you. Unless if you like to keep working on problem number 46 and 47, that's good. If you don't like to take a short break. So it is almost 4:10 right now, 4:15. Thank you. Okay, thank you. The given problem number 46 and 47, start with 47, is giving you the concrete wall consisting of 3 piers. You remember the concept of determining the rigidity. So one of the method is a simplified method where they or told us to locate the piers and the piers are the vertical elements between openings, and the horizontal we call them beams, or in this case we have only one beam, and this is an opening and this is an opening, and there is a lateral force P, and you know the story. How can we determine that? By taking this as fixed, 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 and they are parallel, and add them using H over D. This is called the approximate method of determining the R, the rigidity for a wall with openings. But here he gave us load deflection curve for pier 1 and pier 2 and pier 3. And they said, what is the total force when cracking in elastic yielding begins in pier number 2? Here is pier number 2. This is a curve for pier number 2. What is the inelastic? Inelastic. As you know, and I'll explain this also, the stress strain curve or load deflection curve B delta curve or stress strain curve, when we have a linear portion, we call this as the elastic stage. Elastic stage or elastic range. The moment I start to deviate from linearity, like this, the first deviation, this is inelastic, either a curve or a straight line. Inelastic. So if you look to pier number 2, when this pier number 2, here it is. This is the first deviation from linearity. So if I come here, I draw a vertical line, you will find the pier number 2, when it starts to behave inelastically, it carries 100 kips. But pier number 1 is carrying about 50, and pier number 3 is carrying 40. So this is 100 plus 50 plus 40. When pier number 2 became, when the cracking, okay, yeah, okay, pier number 2. So this is 50 and this is 40. So my answer here is 190 kips. If this is the same number that everybody came up with, or you disagree with me, And if you disagree with me, don't take me to court. Because if you take me to court, we are going to lose. So the answer is D. And I know none of the above. Sometimes I add none of the above to not to challenge you, but to try to pay your attention. I know the actual exam does not have none of the above. Make sense? Okay. Let's go to the problem number 46. And after we finish today's lecture, if you go over these problems and you find that there is something you disagree with me, no problem. We can either send an email to me and I will be glad to go over it one more time. Problem number 46. Give you the same scenario and the same load deflection curve. And he said that the maximum total load P that the concrete can resist is, this beer can carry up to 120 kips. And beer number 1, it can carry up to 100. Plus beer number 3, it can carry up to 60 maximum. So this is 180 and 100. So it is 220, 280 kips. What do you think? Again, oh my God, I'm repeating again, none of the above. Okay, but the 280 will be here. And I believe I have another variation of these problems. So the word is the word maximum, a keyword, total. So I look to the load deflection curve and get the maximum load that can be carried. Go to the previous problem, problem number 45. The same. He said that given the total load B is equal 120 kips, the total deflection at the top of the concrete wall is most nearly. So if the load is given to be at 120 kips, here it is. How much is the deflection in this case? We know the stiffness K is equal P over delta. Do you remember this equation? Which I told you that when we do this in the physics lab, the coil spring, the one you did it in physics, and you apply a load P, and you plot the B delta curve, and the slope is K, which is a stiffness, which is the rise over run is B over delta. So if I can get what is the K for each pier, when the load is 120, will be great. So Any calculations here? I need to get K for peer number 1 and K for peer number 2 and K for peer number 3. Can I do that? Remember, the K is calculated based on the linear portion of the elastic curve, of the stress strain curve or load deflection curve, which is this one here. For peer number 1, peer number 2 at the top here, this is 100 and this is 0.2. So this is equal 100 kips over 0.2, which is the slope of the line. You don't have to pick 100, you can pick 60. But it's much easier for me 100, and this is 0.2, here it is. K2, which is for, this is K2 by the way, sorry. And this K1. K1 is, I have here 80, and this is 0.3. 80, and this is 0.3. And K3, here it is, I have 60 and I have 0.3. 60 and 0.3, which is the slope, which is B over delta, the one I explained before. If you are able to get K1 and K2 and K3, and these are in parallel, so I can get the total delta total for the entire wall as the load P, which is given to be 120, divided by the K total. So for this one here is 100 divided by 0.2 is 0.2, which is 5 times, which is 500. This 80 over 0.3, which is 266.67. And finally, 60.3 divided, which is 200 kib per inch. All these kib per inch because these are inches. So in this case, I can say that the total deflection is equal to 120 kib divided by the 500 plus 266.67 plus the 200, which is the same equation, but I'm solving for the delta instead of K. So in this case, the 500 enter 266.67 plus and 200 plus, inverse that 120 times, I got small number. Delta is equal to 0.12 inches, which is also the none of the above. Maybe next time I will, but you promised me this is the last time you are going to take the exam and you will be ready next time. I don't know when the exams will be offered again, but hopefully very soon. I know some of you may be out of state, some of you in state. It depends from each state, but I think this morning the president closed the entire country. If I'm not state of emergency, I don't know what does it mean. That because the cases are still rising and the number of deaths also still climbing, and I don't know when the country will open again. But if I were you, I will prepare myself as if the exam will be, you are in the second quarter. I don't know if your application has been approved or not. And if your application is already processed and received the okay from the board, California board, to take the exam, try to do your best. And let's conclude this by solving this problem here. This is an easy one. But I need you to go over this and say that, oh, why we did it that way? Why we did it that way? I need you to understand all these things, please, because as I told you, for the last 30 years, I'm doing all my best to make the subject easy and interesting. And again, the teaching at school probably helped me a lot. That's why I'm different from many vendors. I respect all of them. Maybe they are better than me, but I still believe in teaching, and I still believe in presenting the material a little bit different from other vendors, not to show you how to pass and that's it. No, I'm showing you the concept, because I believe if you understand the concept will last with you for long time, and you can't come back easily. By the way, we forget. I cannot deny that we forget. So what is the answer for the last question here? So we can conclude that. And too many problems, and again, the exam or the exams normally, they don't have these problems directly like the one I have here. But believe me, those who bought my books and they use it and they study it in their own, they best just study without taking any course. But you are lucky that again, materials. Okay, you are giving me an answer, my friend. Okay, let me explain it first, and after that I will look to your answer. This is the load deflection curve. This is the rupture or failure. He said that the following complete load deflection curve for 4 building elements are given. Brittle materials. One way we classify materials is to be ductile and brittle. Ductile and brittle. Ductile like steel, concrete, steel, brass, aluminum, with variation of ductility among them, but they are considered ductile. Brittle like concrete, cast iron, chalk, for example. A piece of chalk is very brittle. So, and this is a big issue when we talked about concrete, how to increase the ductility of concrete by 2 things. Do you remember the 2 things that we talked about in concrete chapter? We can increase the ductility, we call it California concrete, by number 1, confinement, number 2, continuity. I need you to remember these 2 terms: confinement plus continuity. Confinement and continuity. So here is one, what is the most brittle? The brittle material like concrete or chalk, or the material that will fail with minimum or small deformation or a small deflection. Small deformation or small deflection. If you look to material number 1 or element number 1, element number 2, element number 3, element number 4, you will find that this is very brittle one. The ductile one, the one it can deform more, ductility. And there is something is called ductility ratio, by the way, or ductility factor. Do you remember this definition? I covered it also in my book, okay, in the glossary or definitions. Oh, sorry, I hit the camera again. Ductility, if you look to, and I refer this to the glossary and definitions I have, which is U sub R. Here it is on page 56 of my book. Ductility factor, which is U sub T over U sub R, which is the toughness, which is the total energy over the resilience, elastic energy. U sub T over U sub R. This is a very important. Ductility. What's ductility? Ductility is a property of yielding, okay, to deformation by an element of a structure in which elastic and plastic deformation are sustained, okay, without significant loss of strength. Ductility is ductile. And this is the whole code, by the way. The whole code, or the seismic codes, since they start to develop these seismic codes, they always look for how can we improve the ductility of the structure. Because the more ductile, the more the energy can be absorbed, the more resistance to seismic force. And this is why the answer is A, which is wall number 1, which is a more brittle material, as indicated here in this. Makes sense. Okay. So let me stop here, and I'm so glad that I survived with you guys from all this, because as I told you last night, I didn't sleep, and I was teaching this morning also for transportation. But I'm glad that I survived all the way until right now. What time is this? 4:30 or 4:38? That's good enough. So please do your best and always communicate with me and solve all the rest of the problems. I was hoping that I can catch these two problems, 40 and 41, which is the drag force, maximum drag force, sometimes cause a little bit of confusion. Okay, but I explained the drag force more than once, but I include these two problems in order to. So please go over these problems and always challenge yourself by solving the questions as if you never saw it before, even if you remember the question, because sometimes we assume that we know the question, but believe me, try to be always ready by assuming that you know nothing about this problem before, or you have never seen it. And this is why the passing rate among the repeat is 50% of the passing rate for the first time taker. The first time taker, they are looking to the subject as they never saw it before. But if I took the exam and I didn't pass it, I missed it by a few things here or there, I say, oh my God, next time I will ace it. And this is why the passing rate among the repeat is 50%. Okay, so I don't like you. So if you took the exam before and you didn't make it, don't worry. You are not the first one and you'll not be the last one. But let us make it, okay, this time to be the last time. Okay, thank you very much again for coming today, and try to do your best. And for those who are enrolled in the class, try to get the maximum benefit of the on-demand. Is very useful for those who used it before. And I hope, and the textbook and the 626, you have good material that has been used for many years, and it did help a lot of engineers. So I hope you are among them that will pass it and forget it. Okay, thank you very much. Pray for me and pray for you. Stay healthy, stay safe, and thank you very much again for coming tonight, and good night, everybody. Bye-bye. And email me if you have any question, please. Okay, let me get the answer here. Thank you. You are very welcome. The answer is A. Okay, Thomas. Okay, thank you very much, Thomas Brown. Okay, thank you very much for attending. So invite your neighbors, invite your friends, invite the kids. The kids can attend for free. Okay, this is a free class. Okay, but don't invite any corona, please. Okay, please. Just joking with you. Okay, we need to get rid of corona. Okay, but invite the kids and invite your neighbor, co-worker. Okay, thank you very much. Bye-bye. Stay safe, please.